The basal ganglia is a system in the brain that's below the cortex, just like the hippocampus is below the cortex and the amygdala is below the cortex. So it's what you call subcortical. It's real important because it allows you to choose the next action you want to do. When I say the basal ganglia allows you to choose the next action you want to do, here's what I don't mean. Like, let's suppose the next action I want to do is have a cookie. Well, it's not really just that the basal ganglia allows me to go ahead and walk to the closet and get the cookie and do the actions. What I mean is that the very decision that sort of pops in my mind of like, what do I want right now? I think I want to get a cookie instead of watching this thing on TV. I'm going to go get a cookie. That the basal ganglia actually allows you to choose which thing you want to do next. So the whole idea of getting a cookie is thanks to the basal ganglia. And then if I decide, okay, now that I had my cookie, now I want to go and watch this program on TV. You know, I've had my cookie, now I'm ready to watch. Well, the idea now, that next goal of watching this particular program on TV, that was also thanks to the basal ganglia. Got a whiteboard here. I think that we can all write down something that you like to do. You want to try and bring things like into this column here, pull things on with your pointer. So, oh, there goes studying neuroscience. Oh well, or someone. Oh, that's nice. I like you. So, guys, let's think about this here. So, really, what the brain's going to do is somehow it's going to keep track of how rewarding it's been for you to go running when the weather's good or when it's daylight. You know, maybe you went running one time and it was like midnight. You know, I don't know why you did that, but you ended up thinking, "Oh, geez, this was dumb. Why to go running at midnight?" And you ended up feeling nervous or whatever. And in the future, you're less likely to even think about it because going running wasn't rewarding. In fact, maybe it was anxiety producing. Cooking lasagna is actually very rewarding when I'm hungry and spending time with family, but not very rewarding under other situations. And what you're going to find is that when you're in these particular situations, that's when this activity comes to mind. So the question is, what's going on from the point of view of the brain? We're looking here at not just the brain, but this is the outer surface. This is the cerebral cortex. And what these arrows are meant to represent is the idea that many different areas of the cerebral cortex are going to send connections to these other brain areas, which are going to loop back to the cerebral cortex. So if you picture, you come up with a goal, you know, maybe cook lasagna. So let's say your brain comes up with this idea. You're hungry, you're with family, and your brain comes up with this goal. Now, so you've got your frontal lobe, parietal lobe, occipital lobe, temporal lobe. You know, the goals are formulated by neuronal activity in the frontal lobe. So in addition to the frontal lobe being important in coming up with, you know, getting you to plan a movement or execute a movement, move your body, there's these anterior parts of the frontal lobe, especially the prefrontal cortex, that are very important in formulating goals. When I say that the frontal lobe is important in activating goals, you know, the idea is that there's certain neurons that become active when you think of that you want to cook lasagna. And there's another set of neurons that's activated when you think about going running and so forth, all right? Now, these parts of the brain that give rise to goals project down to this, what I'm calling right now, brain area 2. In addition to these other parts of the brain that sense that you're hungry, that sense that you're with family, that sort of, you know, perceive the entire situation. So both the goal and the situation, they're all dependent upon neurons in the cortex, and all these neurons are going to send signals down to what I'm going to call right now brain area 2. So let's suppose that your goal was cook lasagna. So let's play with that one for a minute. So brain area 2 actually, so think about this. The fact that you want to cook lasagna and that you're hungry and with family and so forth, it's really your cerebral cortex that's aware of all these things. That's creating the plan, the goal, and that's perceiving the situation. It's not going on in this brain area 2, which I'll give you the punchline is going to be part of the basal ganglia. But brain area 2 knows about what's going on in the cortex because it's receiving information from the cortex. Well, brain area 3 is getting information from brain area 2. Brain area 4 is getting that information, which is all basically this information that came from the cortex to begin with. And if this loop is completed, the brain holds on to that same goal. So what that means is that if you've got this idea, I want to cook lasagna, and these neurons in this part of the brain that are the neurons who, that are activated when you want to cook lasagna, and they activate this brain area, and that leads to this brain area being activated and so forth, and that keeps these neurons active. So the question is, like, what would happen if you didn't have this loop? Like, what would happen if this information going on in the cortex about this goal that you have, what would happen if it sort of got to brain area 2 but didn't get passed on to these other brain areas and you weren't able to quote unquote complete this loop? Well, what it would be that that goal that you had may have appeared in your mind for a split second, but if it wasn't able to complete this loop, you wouldn't have the goal anymore. You would think about doing something else. Maybe it's even so quick that you're not even consciously aware that you had the goal. In order to have a goal that you're aware of and that's online, if you want, for long enough to actually get you to carry it out or think about it, or something like that, you're going to need this basal ganglia loop, this circuit of brain areas to produce activity that sustains that goal. Okay, so this is the way to think about it to begin with. Let me give you another slide, and then I can ask if anybody wants to ask a question. If you generate a goal, the goal is being generated in the cerebral cortex. If this loop doesn't get completed, then the brain abandons the goal, and either sits around with no goal. I don't know if that's possible. I guess it is, or it thinks of some other goal. Let me pull up the PowerPoint. One of the things that I think is really worth being clear on is that if you have neuronal activity in some neurons of the frontal cortex that correspond, say, to the idea of, I don't know, maybe I'll cook up some lasagna now, but maybe you have some other goal that's saying, maybe I will turn on a YouTube video. And you can have both of them generating activity in separate loops. So you could have one loop for the information, which is basically, maybe I'll make some lasagna. And then you've got, say, some other frontal cortical activity that corresponds to the idea of, maybe I'll watch the YouTube video. And this may or may not even be conscious at first. And maybe the YouTube video loop doesn't get past brain area 2. But the maybe I'll cook lasagna loop causes brain area 2 to activate the next areas down the line, and that allows the maybe I'll cook lasagna assembly of neurons, the set of neurons that are active, to stay active and to keep staying active. And so that's the one you end up feeling the desire to do. It's also worth having this clarity on the idea that if you have the set of neurons that corresponds to I'd like to make some lasagna right now, well, from the time these neurons are active, how long do you think it takes for those neurons to activate neurons in brain area 2? Well, think about it. These neurons become active. What does that mean? It means they start firing action potentials and releasing, in this case, glutamate, to the next area down the line. Well, that takes like maybe 10 milliseconds, you know? That is to say, 1 millisecond is 1,000th of a second. 10 milliseconds is like 1/100th of a second. Doesn't matter. The point being that to get from here to here is like a split instant, and to get from here is another split instant, and to go all the way through the loop, it's a very, very quick. Well, in order to say I really want to cook this lasagna, you're going to have to keep that goal in mind for more than 1/10 of a second. You want to keep it in mind for some period of time. So you're going to need lots of iterations through this loop in order to keep that neuronal assembly. A neuronal assembly is a set of neurons that are interconnected. In order to keep that neuronal assembly corresponding to the idea of cooking lasagna active for more than a split second, you're going to need this loop to continue to go around. So Rebecca, go ahead. For the YouTube example, would you even be cognizant of that thought? Right. It could be that these ideas of things you might want to do are conscious, or they will become conscious. But you know, when they first pop up, it may well be that they're not conscious, that in order for them to be conscious, you might need them to stay on for more than 1/100th of a second. Because, I mean, when you think about it, if they don't create an iteration of the loop, they're going to be on for 1/100th of, you know, for a split second, and they're not even going to be able to be on 1/4 of a second later. Well, if you have an idea that lasts for a split second, are you cognizant of it? Maybe not. I don't know, maybe you have a brief flash of a YouTube or that you don't even remember a second later. So the point is, these things could start off not even being conscious. And so it may feel consciously like, you know, what do I want to do? I think I'll make some lasagna. You may not even be aware that your brain also considered some alternatives, you know. It's hard to get at these questions, but theoretically it could start unconsciously. All right. So just for fun, if you imagine, you know, here's Rebecca, who's considering a couple of let's say she's considering one possibility right now. You know, it could be that you first start considering one thing and then you consider another if you don't complete the loop. So let's suppose that Rebecca is considering making, well, let's say the YouTube. Let's suppose that pops into her frontal cortex first. And by the way, you know, a way to think about it is that you've got a bunch of neurons in the frontal cortex. And if you imagine each neuron being one of these boxes that I've got outlined, of course, instead of being, you know, 20 boxes, maybe you'd have 200 million boxes. But the point is, each of the red colored in boxes would be a neuron that's become active, that started firing. So it could be that when Rebecca considers watching a YouTube video, that there's these 3 neurons that are active. And again, each of these could be 1,000 neurons if you want, it doesn't matter. And it could be that, like, when she's thinking about the lasagna, that it's these, you know, these neurons that are active. So it's going to be a different set of neurons who are active that correspond to the different things that pop into your mind, you know, to possibly do. Or another way to put it is, it's the activity of these different groups of neurons that give you these different ideas of things that you want to do. All right. Here's our little thought experiment. Rebecca has got a set of neurons in her frontal cortex that correspond to the idea of, you know, watching this YouTube video. Now we know that within a split second, maybe 1/100th of a second, that activity is going to get to brain area 2, which is brain area 3, brain area 4. And if it gets interrupted, she abandons the idea and chooses something else. Now, suppose for some reason you, the magical wizard, you really would prefer that Rebecca doesn't watch this YouTube video right now. And so you're going to do some neuroscience sorcery. Let's suppose that just as this activity appears in her frontal cortex, the set of neurons, and you know that those neurons are going to send their axons to brain area 2, What if just as this was happening, you waved your magic wand and turned off brain area 2, just for, you wouldn't have to do it for more than a split second. If you did it for 1 second, so that as soon as this activity about, watch the video, gets to brain area 2, well, brain area 2 is offline, so you can't pass the information along. Well, what would happen? You wouldn't complete the goal. So, the fact that we're showing this black line blocking the loop at the very end, it's not to say that you need to somehow prevent brain area 4 from sending the information back to the cortex. I mean, it's true, but you could accomplish that if you interrupted activity in any of these brain areas along the way, along the route, brain area 2 or brain area 3, and so forth. Does that make sense, you guys? Give me a little thumbs up or something if it does, and also feel free to ask questions. Okay. Okay, so let me give you just a second to consider what I have written down here on the board for a moment. Okay, let me just give you a moment to take a look at this PowerPoint as well. Now, we know that brain area 1 is the cerebral cortex. I'm going to ask you guys to get ready to do some memorization. Okay, again, it's only 3 brain areas, and it's going to be useful in terms of us being able to communicate about this. The first brain area is an area you've heard before. It's the striatum. So the striatum receives dopamine. That's going to be a big part of our story. It's also really what we consider the input area of the basal ganglia. So, if the cortex is where you're generating the gall, the cortical neurons activate neurons in the striatum. Well, that's the first stage of the basal ganglia. That's why we call that the basal ganglia input region, all right? Because it gets the information from the cortex, goes to this other area, which we're just going to refer to as the basal ganglia output area. And then that information influences neurons, not going to get into technical details here, of the ventral thalamus. It's a portion of the thalamus. You guys have heard of the thalamus before. This is a special region of the thalamus. It's not an area of the thalamus that's getting auditory, visual, those parts of the thalamus that you learned about in brain-mind experience that carry sensory information. This is a special compartment of the thalamus that's basically dedicated to carrying basal ganglia information through this loop. And then that ventral thalamus is responsible for completing the loop back to the cortex. We're just going to refer to this, as it oftentimes is referred to, as the basal ganglia loop. Hold on a second. I don't want you to hear my mom yelling things. Hold on a second. So here's the thing. First of all, what does it mean for the loop to be interrupted? Why wouldn't a full loop always complete? Why doesn't the loop always become completed? Guys, I'm going to use some neuroscience jargon. Instead of referring to a set of neurons that become active together because they're so interconnected, I'm going to refer to the set of neurons as a neuronal assembly. I'm going to say neuronal assembly, and I'm referring to a group of neurons in the cortex that are all active at the same time. Here's my neuronal assembly for making lasagna. Here's my neuronal assembly, that's active when I want to watch the video. Let me mention something that may be useful for you guys. If you imagine that this is the basal ganglia, the reason we call this the input and the output is that if you were to say draw a box around the basal ganglia, this area, the striatum, is receiving. It's the first area to receive information. It's in this case from the cortex. So that's the input area. And this is the part of the basal ganglia that's going to send information out of the basal ganglia. So that's why we call this the basal ganglia input, and this is the basal ganglia output. if I was somebody where every time a neuronal assembly in my frontal cortex became active, I want to go to Atlantic City to gamble maybe. Nah, I don't want to do that. But if I was somebody nowadays, right? But if I was somebody who once that activity came into my frontal cortex, it starts generating loop activity. And then something else pops into my cortex. I think I want to make lasagna. And that's got this kind of unfettered access to the loop. And then something else. And you've got this kind of multiple loops going through, all sustaining these goals. And now I become someone where like everything I think of is like, yeah, I want to do that. It sounds like mania. And actually, geez, what was it? This guy wasn't manic, this character. What was it called? Ted Danson. You know, where he was the executive. Something to that. So how does the loop get interrupted specifically? You know, the function of the system is so important and so interesting that it makes the details worthwhile. So first of all, let's get our terminology here. A neuron in the striatum, which I'm representing with this red arrow, and of course there will be millions of them, we'll look at one, is a neuron in the striatum is a striatal neuron. All right, everybody cool? Striatal neuron. The inputs to this striatal neuron are going to come from the cortex. So we've got our cortical neurons are sending inputs to the striatal neuron. Well, okay, so here's the first thing. How does the loop get interrupted? Here's the really key way, guys. And I don't know if it disappoints you that it's right at the beginning. It's right in the opening act. You know, the failure to complete the loop is right at the input of the basal ganglia. It's within the striatum. That is to say, it's a failure of the cortical neuron to activate the striatal neuron. Guess which neurotransmitter is released by the cortical neurons? I've got this neuronal assembly representing this particular goal. They release glutamate, and they will excite the striatal neuron, but what type of receptor do I need to have on the striatal neuron in order for this cortical neuron to excite the striatal neuron? AMPA. You got it. AMPA is the workhorse, man. AMPA is doing the hard, heavy lifting. I'm going to give you the key right now, and then we'll fill it in. The real star of the show in the striatum is going to be dopamine. In order to make this a nice, strong synapse, you're going to need the cortical neurons to release glutamate, activate the striatal neuron, and then that's not going to be enough. You're going to now need dopamine, and I'm going to show you next time. Dopamine enters here. Maybe I'll show you real quick before we go. Let me draw it for a second, and the next time I'll show you more nicely. You're going to have dopamine cell bodies. Where are the dopamine cell bodies, guys, that go to the striatum? Yeah, nice. So I'm going to make this a substantia nigra. And these dopamine cell bodies are going to send their axons to the striatum. They're going to release, you know, dopamine. Well, I'm already using red. Let me use green here. Maybe each of these is a little dopamine molecule. And what you're going to need is for the dopamine to go to dopamine receptors. We'll see this next time, just giving you a little preview. You're going to need the glutamate released from the cortical neurons and the dopamine released from the substantia nigra to bind to the striatal neurons at the same time. I'll go take it one step at a time next time. That's going to strengthen the synapse. So I'm going to do something. I want to make lasagna. I activate these cortical neurons. They release glutamate. Glutamate binds to AMPA, makes the neuron fire. You know, there'll be some NMDA receptors and some calcium. That's fine, you know, but that's not what we're going to really focus on because the key thing is dopamine here. All that we need to say is these cortical neurons are going to release glutamate enough to make the striatal neuron fire. And if I end up making lasagna and it's really fun and it makes me really happy or whatever it is, I get a big surge of dopamine. And so now what happens is that dopamine binds to the striatal neuron because there's dopamine receptors also in this neuron. If that happens more or less at the same time that the glutamate is still, at its receptors, then the two together are going to cause the synapse to strengthen. And like always, strengthening the synapse means getting more AMPA receptors. What that means is that in the future, even if I don't have any dopamine, I will have already strengthened the synapse. And when I think about making lasagna, I'm likely to actually do it. You guys know I don't usually breeze through things so quickly, and I'm not doing it here, but that's going to be the picture that we're going to fill in for next time. All right, guys, I'll see you next time. Bye-bye.